Welcome to the course module of Communication Engineering. And in this video, we are going to solve a numerical problem which was asked in GATE 2018. So this particular topic I have already discussed in my lecture classes. So this particular question, if you see, this question is related to square law modulator that we use for AM modulation. So let's try to solve this problem that we have already discussed in the theory. So let's read out this particular statement given in the problem. So here is the problem. Let CT is equals to AC cos 2 pi FCT and MT is equals to cos 2 pi FMT. It is given that this FC is very greater than 5 FM and the signal CT plus MT is applied to the input of a nonlinear device whose output V output T is related to the V input T as V output T equals to A V input T plus B VI square T, where A and B are positive constants. The output of the nonlinear device is passed through an ideal band pass filter with center frequency FC and bandwidth 3 FM. To produce an amplitude modulated wave, if it is desired to have the sideband power of AM wave to be half of the carrier power, then we have to find out this ratio A by B. Okay. So based on this problem, let's try to solve how to get this result A by B. So as per the given problem here, you can see this carrier wave is given as CT, and this is our message signal MT equals to cos 2 pi FMT. So based on this problem, if we draw the block diagram, then this block diagram will be something like this. Okay. So first of all, what we have to do is we have to apply the input signal. Okay, because here it is written like the signal CT plus MT is applied to the input of the nonlinear device. So let us suppose we have the nonlinear device and this input VIT will be applied to this particular nonlinear device. Okay. Then this output of this nonlinear device is related with this V input T is equals to this particular relationship. Okay, so that we have written over here. So here it is also mentioned that the band pass filter is having certain central frequency, and that central frequency is FC. Okay, and its bandwidth is 3 FM. Okay, so let's say that we have the ideal band pass filter and its central frequency is FC and its bandwidth is 3 FM. So that it's 3 dB cutoff frequency, or you can say that the cutoff frequency, because it is ideal band pass filter, so its cutoff frequency will be FC plus 1.5 FM, and lower side this frequency will be FC minus 1.5 FM. Okay, therefore its bandwidth will become 3 FM and its central frequency is FC. So now just try to see this V input, we have to apply it as CT plus MT. Okay. So here we can apply this V input T equals to CT plus MT. And now we can substitute for this CT value. Okay. So here we can say this VIT is equals to AC cos 2 pi FCT plus MT. So here is the CT value. So right now I'm not substituting for MT. Okay. So first I will solve this equation, and then at the end we will substitute for MT equals to cos 2 pi FMT. So here we can get the expression for this V output T when this signal V input T will pass through the nonlinear device. So here you can see this simple relationship of V output T with the V input T. So if you substitute for V input T, this can be easily obtained AMT plus AAC cos 2 pi FCT plus B M square T plus AC square cos square 2 pi FCT plus 2AC MT cos 2 pi FCT. Okay, so this B is this particular factor, which is common to this all factors inside this parenthesis, right? So here we can see this equation. This equation can further be rewritten, okay? And we can modify this, and this can be rewritten as this form, okay? So in this form, we have just taken certain factors like here we have this particular term AC cos 2 pi FCT, okay? AAC cos 2 pi FCT. I have taken this term, and then I have taken mt cos 2 pi FCT term. Okay, so this is the another term which is your mt cos 2 pi FCT. So if we expand this, so this will be multiplied with b also. Okay, so here we are going to get this 2b, 2b multiplied with AC mt cos 2 pi FCT, right? So if we take this AAC common, you are going to get this particular term, right? So AAC plus 1 2b by A mt cos 2 pi FCT. So after considering this term and this term, okay. And then the rest of the terms is written over here, AMT BM square T plus BAC square cos square 2 pi FCT. So now if this is the signal, okay, if we pass it through the band pass filter, right? Here we can easily see that because this band pass filter is having its central frequency FC and its bandwidth is 3 FM, right? Then this empty signal empty will be rejected by the filter. So why it will be rejected by the filter? Because empty is having its frequency component F equals to at FM, okay? So its frequency is FM. So in the spectrum, you will be getting a spectrum F equals to FFM, FM, okay? FM, right? So this is also given, one more condition is given that this FC is much greater than 5 FM, right? So obviously this F equals to FM will be outside the passband of your band pass filter. So this empty will be rejected. Obviously, this m square t is also going to be rejected. Okay. So if you square this signal cos square 2 pi fmt, then obviously we are going to get one DC term plus a frequency component at f equals to 2 FM, right? So because of this condition, this 2 FM frequency component due to this bm square t will also be rejected. Okay. Similarly, cos square 2 pi FCT will give you one DC term, and another frequency component will be at f equals to 2 FC, right? And again, it will be coming out of the passband of your band pass filter, and therefore this all three terms will be rejected by your band pass filter. So if you see this output of the band pass filter, right? So after passing the signal, this output of your band pass filter, if it is represented by V output T, then this signal obviously will be this particular signal, right? So here you can see this particular signal is actually, if you see, this is having one carrier component at f equals to fc, which is the central frequency of your band pass filter. And this multiplication, right? This multiplication mt with cos 2 pi fct will give you a frequency component at fc at f equals to fc plus fm and fc f equals to fc minus fm. Okay. And because it will come inside the passband of your band pass filter, therefore this component will be passed through the band pass filter, and rest of the components will be rejected. So here we are getting this particular term, right? So now we can see this is the condition, right? So this is your equation. So now we can substitute for mt equals to cos 2 pi fmt, right? So here we have cos 2 pi fmt. So now we can further solve this equation. We can expand this expression. So if we expand this expression, you will be able to see we are getting one carrier term, and here we are getting the multiplication of your carrier with the given masses signal. Okay. So here, if you further expand this particular expression, we can see that we are going to get the upper sideband and we are going to get the lower sideband, right? So here we have to just use the 2 cos A cos B formula, okay, and by that we can get this particular equation, right? So here we can see this particular equation. This is your carrier part, this is your upper sideband, and this is your lower sideband, okay? So Now, if you see this condition, right, here it is asked that if it is desired to have the sideband power of the AM wave to be half of the carrier power, okay? So first we have to calculate the power of the carrier wave, and then we have to calculate the power of your sideband power, right? So here is our carrier, right? And here is the amplitude of the carrier is AAC, right? So you must aware that if we have any signal, if it is having uh, like its amplitude is a cos 2 pi fmt, if its amplitude is a, then its power will be a square by 2. Okay. So the same fact we can use here to calculate the power of the carrier. So here its amplitude is AAC, right? So it will become a square AC square by 2. And we have to also calculate the sideband power. So sideband power will be the power available in the upper sideband plus power available in the lower sideband, right? So here we can calculate this. Okay, so this value will be b square AC square by 2. And again, here we are again going to get b square AC square by 2. So ultimately, this sideband power that we are going to get is b square AC square by 2. So as per the given problem, right, here it is mentioned that it is desired to have the sideband power of the AM wave to be half of the carrier power, right? So we have to just put this condition, the sideband power is equals to PC by 2, okay, half of the carrier power. So now you just substitute this equation, PSB equals to B square AC square, okay, and PC equals to A square AC square by 2, okay. So because of this factor 2, you will be getting this factor equals to 4, right? So now you can easily calculate this ratio A by B, okay, because we have to calculate this ratio. So this AC square will be cancelled out. And now you will be able to show this A by B is equals to 2. So therefore, the answer for this problem is your option D, right? So this way we can solve this problem. So those who have not watched my uh, lecture video about the square law modulator, okay, please go through that video. Uh, then only you will be able to follow this particular solution clearly. Okay. So thank you for watching this video. If you have any query, please ask me by posting your comments. So thank you for watching this video.